Welcome to this explainer. Today we're going to take a super familiar shape, something you probably doodled in the margins of your grade school notebooks, and we're going to completely unpack it to reveal some genuinely mind-bending physical and mathematical secrets.
So, let's just dive right in with a pretty wild question. What exactly connects ancient pyramids, infinite fractals, and the literal globe we live on? I mean, how does that basic everyday shape bridge the gap between thousands of years old architectural marvels and the absolute outer limits of non-Euclidean space? Well, the answer, as we're going to see, is the equilateral triangle.
Okay, starting with the absolute basics here. By definition, an equilateral triangle is a regular polygon. It's got 3 equal sides and 3 equal 60-degree interior angles. But what's actually remarkable about this, what makes it special, is that it is the only polygon where its entire structure is completely locked in by knowing just a single side length. Literally, if you know one side, you know the whole shebang.
And because of that beautiful simplicity, it's incredibly easy to build from scratch. People have been using this exact method since antiquity to create perfect symmetry. You basically just take a line segment, lock a compass to that exact width to guarantee your sides are congruent, and draw a couple of intersecting arcs. Where those arcs meet, boom, you've got perfect 60-degree angles.
Now, that simple structure translates into a really elegant area formula. If you use Pythagoras' theorem to find the height, the area formula just boils down to the square root of 3 divided by 4 times the side length squared. But hey, this elegance isn't just trapped in some dusty math textbook, right? It translates beautifully out into the real physical world.
Let's actually look at that physical world for a second. That perfect symmetry makes the triangle the absolute, undisputed heavyweight champion of architectural stability. Think about it. It has a heavy, solid base and a pinnacle that efficiently handles and distributes weight completely evenly, downward and outward. So you end up with incredible structural integrity because there are 0 uneven pressure points.
And you can see this strength at play in structures that have literally survived millennia. Look at the Great Pyramid of Giza. It's been standing for over 4,000 years, and each of its 4 faces is an equilateral triangle, relying on that impeccable weight distribution we just talked about. From those ancient pyramids all the way to the isosceles plots of the East Building in DC or New York's iconic Flatiron Building, triangles are just everywhere.
Basically, architecture fundamentally relies on these shapes as essential tools. Because they provide such unyielding strength and stability, you'll find them supporting everything. We're talking everything from a cozy residential A-frame cabin to those massive steel diagonal grids holding up Manhattan's Hearst Tower. It's a real game changer for engineering.
All right, let's shift our perspective a bit here. We're going to dive into the hidden elegance inside pure geometry by looking at Morley's trisector theorem. This was actually discovered relatively recently, in 1899 by Frank Morley, and it offers this surprisingly beautiful result that, honestly, feels almost like magic.
So imagine taking any random, totally irregular, completely messy triangle. Now draw the adjacent angle trisectors. Basically, all you're doing is splitting each of the 3 interior angles into 3 equal parts, and then you draw lines to see exactly where they intersect inside that triangle.
And here is the crucial point, the big magical reveal. Those intersection points, they invariably form a perfect equilateral triangle right in the center. Seriously, no way around it. It does not matter how chaotic or skewed or weird the original triangle is, it proves that perfect order exists right in the middle of geometric chaos. It's just a stunning piece of math.
And then there's Napoleon's theorem. And yeah, actually, that's named after the Napoleon Bonaparte, who apparently had a little side hustle as a math enthusiast. This theorem shows that if you build equilateral triangles on the outside edges of any triangle and then connect their center points, those centers will form, you guessed it, yet another perfect equilateral triangle. No matter what you start with, this perfect shape just keeps emerging from the randomness.
Okay, but now it's time to really start bending the rules of reality. We are officially leaving the flat, safe planes of Euclidean geometry and stepping into spherical geometry. You know that on a flat piece of paper, a triangle's interior angles always add up to exactly 180 degrees, right? Well, on a sphere, that sum is always greater than 180 degrees. And get this, it can actually be up to 540 degrees.
See, in spherical geometry, the basic building blocks are points and great circles instead of straight lines. If you're on a globe, the shortest path between 2 points isn't a straight line tunneling through the Earth, it's a curve running along a great circle. Think of the equator. And when these great circles intersect to form triangles, they completely, literally shatter Euclid's classical rules of geometry. Because the rules completely change on a curved surface, a spherical triangle's area is actually proportional to its angle sum. To put that into perspective, imagine drawing a massive triangle on the Earth. You start at the North Pole, draw a line straight down to the equator, go a quarter way along the equator, and head straight back up to the pole. You have just created three 90-degree angles. That's 270 degrees sitting inside a single triangle. Crazy, right?
So, from the vastness of the globe, let's scale things up to the infinite paradox of the Koch snowflake. This is a totally mind-bending fractal that was introduced in a 1904 paper, and it pushes the equilateral triangle to its absolute mathematical limits. You construct it by endlessly repeating just three simple, deliberate steps. First, you take the sides of an equilateral triangle and divide them into three equal segments. Then, draw a smaller outward equilateral triangle right on the middle segment. Finally, remove that middle baseline. By repeating this infinitely, just constantly adding smaller and smaller triangles to the perimeter, we end up creating a shape that completely defies standard intuition. Now, you'd naturally think that as you repeat this process out to infinity, the area of the shape would just, explode out of control. But it doesn't. Miraculously, the total area of the Koch snowflake converges to exactly 8/5 the area of your original starting triangle.
So what you should really take away from this is the ultimate geometric paradox. The Koch snowflake encloses a strictly finite area, like it never grows beyond a certain boundary. Yet, because we keep adding smaller and smaller bumps to the edge forever, its perimeter is infinitely long. It's like you could never ever finish drawing its outline, but you could easily buy a can of paint and paint the inside. And listen, this isn't just some fun theoretical trick, it actually has massive real-world value. Engineers literally use this infinite perimeter property in limited spaces to design highly efficient cellular antennas. By folding the antenna wire into a fractal shape, they can maximize electromagnetic reception in an incredibly tiny space. It's even used for advanced acoustic surfaces to diffuse sound in car cabins. As we wrap up this explainer, seeing how the equilateral triangle spans from ancient pyramids all the way to fractal infinity, it really leaves us wondering, right? If a shape this basic can hold infinity and bend the very rules of space, what other profound, rule-breaking secrets are hiding inside the simple shapes we take for granted every single day? Thanks for joining me on this deep dive, and keep questioning the world around you.